Kususangpo, I'm Dojinobu, and today I will be presenting a lesson on the topic carboxylic acid and its derivatives. This lesson pertains to Key Stage 5 for classes 11 and 12 chemistry. Now before I present to you all the details of the lesson, first of all let's go and look at what are the objectives of these lessons. The first objective of the lesson says define carboxylic acid and its derivatives. The second, give examples of common carboxylic acid and its derivatives. So after defining, you must be able to give some of the examples of common carboxylic acid and its derivatives. Then third objective is by the end of the lesson, student must be able to write the chemical formula of those common carboxylic acids and its derivatives. And finally, students at the end of the lessons must be able to list the common uses of the derivatives of carboxylic acids. So these are the 4 lesson objectives we have for today. Okay, now let's go in detail. First, carboxylic acids. What is carboxylic acid? So we have come across so many carboxylic acid in our daily life. But before I give you the definition of what carboxylic acid is, let's look at some of the examples of common carboxylic acid that we come across in our day-to-day life. Okay, first we have a formic acid. Then second, we have acetic acid. Third, butyric acid. Then fourth, benzoic acid. Now if you look at the structure of all these acids, there are some structure which is common to all the acids. Can you identify it? Okay, the common structure you can see in all this acid is COOH. In first, formic acid, acetic acid, butyric acid and benzoic acid. So in all these 4 acids you will see a common structure COOH. Now what is COOH? What is its name? And what are its function? So now COOH, it is known by the name known as carboxyl group, and it is a functional group. Now you have all the information about what COOH is. So finally you need to come up with a definition. And the definition of carboxylic acid says carboxylic acids are organic compounds which contain carboxyl group as the functional group. So if you look back at the examples, you see that all this carboxylic acid contains carboxyl group, and this carboxyl group acts as a functional group. Now more examples of common carboxylic acid. Okay, let's say oxalic acid, then citric acid. Now if you look at those examples, you can see that carboxylic acid doesn't mean it should have only one COOH or carboxyl group. It can have either 2 or 3. Now if you look at this structure, you will see that carboxyl group is the functional group of carboxylic acid, and all the properties shown by carboxylic acid depends upon this carboxyl group COOH. So next what we are going to look is, we are going to look at the nature of the carboxyl group. So nature of carboxyl group COOH. So if I write down the structural formula of COOH or carboxyl group, you will see that this carboxyl group is made up of 2 functional groups. One, C double bond O is known as a carbonyl group, and OH is known as a hydroxyl group. And C double bond comes from a carbonyl group which is present in aldehydes and ketones. And OH, known as a hydroxyl group, is present in alcohols. So therefore we can see that carboxyl or carboxylic acid which contains carboxyl group is made up of carbonyl group and a alcohol group. Now if you look at the name carboxyl group, you can also see that the word carb comes from carbonyl and oxyl comes from hydroxyl. So therefore carboxyl is a combination of a carbonyl group as well as a hydroxyl group. Now since this carboxyl group is a combination of a carbonyl group and a hydroxyl group, we expect this carboxyl group to show the characteristics of both carbonyl group and hydroxyl group because it is made up of these 2 groups. But studies have shown that this does not happen in reality. So in reality, what people have found out is they have found out that this carboxyl group, although it is made up of this carbonyl group as well as hydroxyl group, it doesn't show the characteristics of either of them. So what studies have found out is that this carboxyl group acts as an independent functional group, and it has got separate it shows separate behavior, or it has its own characteristics. Now before I go on with the next slide, let's see, there's an important point that we must know. So it says carbonyl group is polar in nature due to negative inductive effect of oxygen. So this is the information that we must keep at the back of our mind when we study about the chemical properties of this carboxylic acid and its derivatives. So what does it mean? So in both the cases, you can see the carbon is linked to oxygen through double bond, and one is a sigma bond and another is a pi bond. Now between carbon and oxygen, the shared pair of electron is pulled towards oxygen because of the higher electronegativity of oxygen, and as a result, oxygen on the carbonyl develops a slight negative charge and the carbon develops a slight positive charge. So therefore, since there is a negative charge as well as positive charge, this carbonyl group is polar in nature. Okay, then next let's see the classification of carboxylic acids. So carboxylic acids can be classified in different manner. So I'll present to you the two types of classification. So first classification of carboxylic acid is based on the nature of group attached to carboxyl group. So based on the nature of group attached to carboxyl group, this carboxylic acid can be divided into two categories known as aliphatic carboxylic acids and aromatic carboxylic acids. What is aliphatic carboxylic acids? So here the carboxyl group is attached to alkyl group or hydrogen atom. Now this is the carboxyl group, and if you look at the carbon, you can see that the one bond of carbon is still vacant, and to that vacant site we can attach either the alkyl group represented by the letter R or hydrogen, and in case it is replaced by hydrogen, what we get is a common carboxylic acid known as a formic acid, and in case if the alkyl group is a methyl group, then we get CH3COOH known as a acetic acid. Now coming to aromatic carboxylic acid. So here also the group attached is a alkyl group, aryl group. It's a group attached is a aryl group, and the aryl group are represented by a general formula AR. So when AR is attached to this carboxyl group, so what we get is ArCOOH as the general formula. Now specifically, let's say we have COOH, a carboxyl group, and to that one if we add a benzyl group, then what we get is a benzoic acid. Then in case if we add a toluene, when we add a toluene, then what we get is orthotoluic acids. So if you look at the structure of aliphatic acid and aromatic acid, then you can make out the differences. So the difference is based on the nature of group attached to carboxyl group. So this is the first classification of carboxylic acids. Okay, then let's go with the second classification of carboxylic acids. So second classification, the criteria it says is based on the number of carboxylic group that is present in an acid. In one molecule of an acid, we have to count how many carboxyl groups are present, and based on the number of carboxyl group that is present on an acid, we can classify them as monocarboxylic acid, dicarboxylic acid or tricarboxylic acids. So monocarboxylic acid, example acetic acid, dicarboxylic acid, let's say oxalic acid, tricarboxylic acid, citric acid. Now by looking at the structure of these acids, you can make out why first one acetic acid known as monocarboxylic acid, and likewise. So if you look at acetic acid, there is only one carboxyl group, so it known as mono. Mono means one. Then you can see in oxalic acid we have two carboxyl group known as di, and in citric acid we can see there are three carboxyl groups, so it's known as a tricarboxylic acid. And more examples, benzoic acid, only one COOH or carboxyl group. Then we have phthalic acid, two carboxyl group. Then we have tricarbolic acid having three carboxyl group. So this is the classification based on the number of carboxyl group present in an acid. So here is a question for you to explore further. First question is quite easy. So what you need to do is you have to write down the IUPAC name of the following carboxylic acids: formic acids, acetic acid, butyric acid, benzoic acid, oxalic acid, and citric acid. So these are the carboxylic acids names of a common names. So what you need to do is you have to write down the IUPAC name of all these acids. Then another one, name the acid that is found in bee sting. So when you are stung by a bee, then what happens? There is an allergic reaction happening on our skins and our skin swells. And this is because of some of the acid present in that one. So I want you to find out what is the acid that's present on those bees. So this is what you must complete. Okay, then next let's go derivatives of carboxylic acid. So here, before you understand what is meant by derivatives, you must understand that carboxylic acid is like a trunk of a tree. Then from the trunk of the tree, so many branches come out, and these branches are known as the derivatives of carboxylic acid. So this is the general formula of carboxylic acids, and to study the derivatives of carboxylic acids, what we need to do is we need to focus on the hydroxyl group that is present on carboxylic acid. And you must remember that this hydroxyl group is expandable. That means it can be removed and replaced with some other substances. So first of all, let's say that this OH is being removed and it is being replaced by halogen, the generally represented as X, such as chlorine, bromine, and iodine. So if OH is replaced by halogens such as chloride, bromide, or iodide, then what we get is we get a general formula RCOX, and the general name of this one is known as acyl halide. So acyl halide is the first derivative of carboxylic acid. Then second, if you remove this OH and replace it with amide group NH2, then what we get is we get RCONH2, and this RCONH2 is known as acid amide. Then similarly, if we replace OH with OR known as alkoxy group, then what we get is we get a derivative whose general formula is RCOOR, known as esters. Then finally, if OH is being replaced by RCOO, then we get RCOOR, known as acid anhydride, and this acid anhydride is the general name of the compound in which OH is being replaced. So we can see that there are 4 derivatives of carboxylic acid, and we are going to study each of them. So before we study, now what we need to do is we need to define what's meant by derivatives of carboxylic acids. So as I have shown in the examples, it says the compounds obtained by replacement of OH part of the carboxylic group of the carboxylic acid. So OH is being replaced by certain groups such as halogen, amide, anhydride, or alkoxy group, then we get a new compound, and these new compounds are known as the derivatives of carboxylic acids. So as I said earlier, we are going to study each of the derivatives in detail. So first derivative we are going to study is acyl halides, or also known as acid halides. So general formula is RCOX. So RCOX, where OH group of hydroxyl group of acid is being replaced by halogen. So where R is an alkyl group and X is a halogen such as chloride, bromide, or iodide. Now we are going to replace each of them with particular agents. For example, let's say the alkyl group is CH3 and the X, the halogen, is chloride. Then if we replace R with CH3 and X with Cl, then what we get is we get CH3COCl, known as acetyl chloride. This acetyl chloride is common name. Then why it is known as acetyl chloride? To know its name, we have to look back to its parent acid, acetic acid. So parent acid is CH3COOH, which is an acetic acid. And from that acetic acid, what we have done is we have removed OH and then replaced it with Cl. So when OH from acetic acid is removed and is replaced with Cl, then what we get is we get acyl halide known as acetyl chloride. Okay, now let's go with how acetyl chloride is prepared in the lab. So basically it says there are 3 methods in which acetyl chloride can be prepared in the lab depending upon the availability of the resources. So first it says you react acetic acid with phosphorus pentachloride, then you get acetyl chloride. And second method is you react acetic acid again with phosphorus trichloride, here also you get acetyl chloride. And third method is you can react acetic acid with thionyl chloride, and here also you get acetyl chloride. So basically what we have is we have 3 methods. Now which method to use, as I said, it depends upon the availability of the resources and all those things. Now out of these 3 method, in case let's say that all the resources are present available, then what we need to make is we need to make a judicious decision of which method to be used. So my question here is for you to explore yourself, which among the 3 methods is the best and justify. So that means you have 3 methods. So out of these 3 methods, you have to choose which method is the best, and then you have to justify why that particular method is good. So this is a question for you all to explore further. Okay, then next we'll go with the properties of acetyl chloride. So when we say properties, first of all we always go with the physical properties. So let's say physical properties of acetyl chloride. It says acetyl chloride has got a pungent odor. So it has got a pungent smell, and it also says it's a lacrimator. That means acetyl chloride excites our lacrimal gland in the eye and it produces tears. Then next, second physical property is boiling point. It says that boiling point of acetyl chloride is lower than its parent acid, that is acetic acid. Okay, this is the parent acid, acetic acid. Molecular mass is 60. Boiling point 391 Kelvin, which is around 118 degrees Celsius. And we have acetyl chloride, molecular mass 78.5, and boiling point is 324 Kelvin or 51 degrees Celsius. Now if you compare the molecular mass as well as the boiling point, you can see there is an inverse relationship. So normally what we do is, normally in chemistry what happens is, higher the molecular mass, then higher the boiling point. But here you can see that acetyl chloride has got higher molecular mass compared to the molecular mass of acetic acid. Yet you can see the boiling point of acetyl chloride is low. What could be the reason? So this is what you need to explore yourself. Boiling point of acetyl chloride is lower than that of acetic acid despite acetyl chloride having higher molecular mass. Why? So explore yourself. Okay, next we have a chemical properties of acetyl chloride, and this is the general this is the formula of acetyl chloride, CH3COCl. Now here, to understand the chemical properties of acetyl chloride, what we need to focus is we need to focus our attention on the bond between the carbon and the chlorine, and the carbon that is being attached to chlorine in acetyl chloride is known as a acyl carbon. So we need to focus our bond here between carbon and chlorine. And between carbon and chlorine is a covalent bond. There is a shared pair of electron. So one electron comes from the chlorine, another electron comes from carbon. They share and form a covalent bond. Now, in our previous classes, we have learned that the shared pair of electron, whether the shared pair of electron will remain exactly in the middle, or it will move towards carbon, or it will slightly move towards chlorine, depend upon the electronegativity of that. Electronegativity of those atoms. So in this case, we know chlorine has got higher electronegativity, and electronegativity, you know, is a tendency of an atom to pull the shared pair of electron towards itself. So since chlorine has got higher electronegativity, it will pull the shared pair of electron towards itself. So when it pulls the shared pair of electron towards chlorine, then we know that chlorine will develop a slight negative charge because of the close proximity of that atom towards chlorine. And as a result, although carbon is not totally losing the electron, but since the distance from the electron is increased, then what would happen is carbon would develop a slight positive charge. And if you remember back in the to the beginning of the session, I have said that carbonyl group is already polarized. That means carbon had already got a slight positive charge. Now on top of that one, because of the difference in the electronegativity between chlorine and carbon, the positive charge or the magnitude of positive charge on carbon has increased a lot. So if I magnify it, see that the carbon in the center, known as the acyl carbon, has got a large positive charge. Number one, because of the negative inductive effect of the oxygen that I presented earlier, and number two, because of the difference in the electronegativity between chlorine and carbon. And because of the high magnitude of positive charge on carbon, then what happens is this acyl carbon is easily attacked even by weak nucleophiles such as water and alcohol. And that means these nucleophiles can easily go and get attached to this carbon, and that is why acyl chlorides are most reactive of all the derivatives of carboxylic acid. Because here we must know a point, it says the reactivity of the derivatives of carboxylic acid depend on the magnitude of positive charge on the acyl carbon. So because of the presence of chlorine, the magnitude of positive charge on the carbon has increased a lot. And because of the increase in the magnitude of the positive charge on the carbon, then this carbon is very susceptible to be attacked by nucleophiles or by even by weak nucleophiles such as water and alcohol. And that is why it becomes highly reactive compared to other three derivatives of carboxylic acids. So this is with regard to the first derivatives. The second derivatives of carboxylic acid is known as acid amide, where OH group is being replaced by NH2. So we get a general formula known as RCONH2. So similar to that one, this R is an alkyl group, and in case the R is CH3, then what we get is CH3CONH2, known as acetamide. And how did we get the name acetamide? We have to look back to the parent acid. So parent acid is acetic acid, and from that acetic acid you have removed the OH and it's being replaced by NH2, then you get a name known as acetamide. Then the physical properties of acetamide. So first thing, to study the physical properties of acetamide, let's go with the boiling point of acetamide compared to its parent acids. So let's say parent acid is acetic acid, molecular mass 60, boiling point 391 Kelvin or 118 degrees Celsius. Now if you look at acetamide, molecular mass is 59, lower than the molecular mass of acetic acid, but boiling point is way higher than the boiling point of acetic acid. Now in previous example we have seen that higher molecular mass, lower boiling point, but here we see that lower molecular mass, higher boiling point. What could be the reason? So if you know the reason to the previous question, here it will be similar. So therefore I want you to explore further why the boiling point of acetamide is higher than the acetic acid, although its molecular mass is less, because as I've said, higher the molecular mass, higher the boiling point, but here it's just happening in reverse. So I want you to explore further. Okay, let's look at the chemical properties of acetamide. And as I said, the chemical properties of derivatives of carboxylic acid depend on the magnitude of positive charge present on the carbon. So here what happens is, the amide, the nitrogen of the amide contains a lone pair of electron, and this lone pair of electron can be delocalized, and as a result of the delocalization of that lone pair of electron, then what happens is the magnitude of positive charge on the carbonyl carbon reduces. And because of the reduction in the magnitude of positive charge on carbon, then what happened? This acetamide does not readily undergo these reactions. So therefore, what they have concluded is, we conclude that amides are less reactive of all the derivatives towards nucleophile acyl substitution reaction, and this is because of the reduction in the magnitude of positive charge on the carbon, which is caused by delocalization of lone pair of electron present on the nitrogen of the amide. Okay, now one specific example of chemical property of acetamide is Hofmann's bromamide reaction. Okay, let's say you have a acetamide. So when acetamide is reacted with or heated with bromine in presence of alkali, for example potassium hydroxide, then what we get is we get a primary amine and along with some other products. So now the production of this primary amine with the help of this acetamide when it is heated with bromine and potassium hydroxide, this reaction is known as a Hofmann's bromamide reaction. Now here what we need to focus is we need to focus on the organic part of the reaction on reactant as well as on product side. On reactant side we have a parent amide known as acetamide. If you look at carefully at acetamide, you will see that this acetamide has got 2 carbons. Whereas if you look at the product side, that's methanamine, you will see there's only 1 carbon. So from 2 carbons it has become 1 carbon. Now to remove this carbon, it is not the way, it cannot be done like we do with so many other activities in our daily life. For example, if we want to remove husk from our rice, we simply pick out with a finger. And if you want to remove this carbon and reduce the number of carbon, we cannot use a tweezer and then remove the carbon. So what we need to do is, so for this we need to let it undergo a reaction, and this reaction in which the number of carbon is being reduced is known as a Hofmann's bromamide reaction. So therefore we have a very specific definition which says the production of an amine or a primary amine with 1 carbon atom less than the parent amide when it is heated with bromine in presence of alkali such as potassium hydroxide is known as a Hofmann's bromamide reaction. And this, the other name of this Hofmann's bromamide reaction is also known as Hofmann's degradation reaction. And why it's known as a degradation reaction? Because the number of carbon is being reduced. So degradation here can be synonymous with reduction in the number of carbon. So the importance of these reactions. This reaction, as I said, also known as Hofmann's degradation reaction. This reaction is used in converting higher member of a family to a lower homologue. So if you have a carbon having, if you have an organic compound having 4 carbon, and if you want to convert it to 3 carbon, then we can use this Hofmann's degradation method, provided that the reactant is a amide and the product we get is a amine. So this is one chemical property of amide. Now let's go to the third derivatives of carboxylic acid. The third derivative of carboxylic acid is known as an ester, and the general formula of ester is RCOOR. And here 2 R's can be similar or it can be different. So if you have a similar R, then what we get is we get a simple ester, whereas if 2 R's are different, then we get a mixed ester. So for example, okay, let's say RCOOR, where R is an alkyl group and OR is known as alkoxy group, and alkoxy group O stands for oxygen and R dash stands for alkyl group. Okay, let's say that for example the R is CH3, the methyl group, and R dash is a ethyl C2H5. The ester we get is CH3COO C2H5. So this is the ester we are getting. Now let's go and see how these esters are being prepared in a lab. So this is a general equation where esters are being prepared. So to prepare an ester, what we need is, number 1, we need a carboxylic acids. And when this carboxylic acid reacts with alcohol in presence of concentrated sulfuric acid, what we get is we get ester and a water. And since this reaction produces esters along with the water, the reaction, the general name of the reaction is known as esterification reaction. And if you look at the reaction there, you can see there is a double-headed arrow which indicates that this reaction is highly reversible. So that means whatever esters and water is being produced, these two will react and give back the reactant. Okay, now let's go with specific example. For example, the carboxylic acid we have is acetic acid, and the alcohol we are using is ethyl alcohol. So I have rearranged the molecular structure of ethyl alcohol so that the product, we are clear with the product that we get. So here OH of the acetic acid combines with H of the ethyl alcohol. Remember that it is the OH of the acetic acid and H of the ethyl alcohol which reacts to give you ethyl acetate, which is an ester and a molecule of water. And as I said, this reaction is highly reversible. In case if you want to produce ethyl acetate, It's very difficult to get ethyl acetate if the reversibility of the reaction is not checked or not prevented or not minimized. So I want you to find out or explore yourself, how can the reversibility of the esterification reaction be checked, or how can the reversibility of this reaction be minimized or prevented? So this is one question which you need to explore. And now second question, as I've shown earlier, to produce water we are using, or there is OH from the acetic acid, and it's the H of the ethyl alcohol that gives a water in this reaction. Now the next question is, there is also a possibility where that there is OH of the alcohol and H of the acid, which will again combine to give you water, but this is not happening. So I want to find out why OH of the alcohol and H of the acid is not combining in this reaction to give a water. So these are the two questions I want you to explore further. Okay, now let's go with the properties of esters. So number one, physical properties. It says esters of lower carboxylic acid have a pleasant smell and taste, and that is why these esters are mostly used in flavoring, used as an artificial flavor in most of the food. So for example, okay, let's say we have banana, and banana has got certain taste and certain smell, and that is because it contains an ester known as amyl acetate. And similarly, let's say we have apricot. So apricot has got certain smell and certain pleasant smell and taste is because of the ester known as amyl butyrate, and similarly pineapple ethyl butyrate, and then oranges known as octyl butyrate. So almost all the fruits which have got pleasant smell and pleasant taste have got these esters. So these are some of the examples of the esters that is present in these fruits. Now, okay, now let's go with chemical properties of esters. So the first chemical properties of ester is alkaline hydrolysis of ester. So that means what happens to a ester when you react with alkali, such as sodium hydroxide or potassium hydroxide. Okay, let's say you take an ester known as ethyl acetate. So when it reacts with sodium hydroxide, then what we get is we get sodium acetate and ethyl alcohol. So you can see that the sodium acetate is a salt that is being produced by reacting ester, ethyl acetate and sodium hydroxide. Now in case if you look at sodium acetate, you can see the parent acid is acetic acid. And in case if you use that, if you use higher fatty acid in case of instead of this acetic acid, then what we get is we get a salt, and those salt of higher fatty acids are known as a soap, the soap that we use every day, and the reaction is known as a saponification, because in Greek the soap is known as sap, and this is what we are going to study next. And to study how the soaps are being manufactured, first of all what we need to do is we need to understand what's meant by oils and fats. And oils and fats, definition it says they are the esters, but they are the esters of higher fatty acids, not a common carboxylic acid. So they are fats of higher fatty acids. For example, or let's say in a previous slide we have seen that when alcohol reacts with carboxylic acid, you get an esters and water. And to produce oils and fat, what we have is we have glycerol, and glycerol is nothing but it's alcohol, trihydric alcohol having 3 OH group. So when it reacts with stearic acid, so stearic acid formula C17H35COOH, so we have 3 molecules of stearic acid. So this stearic acid is a carboxylic acid, but it's a carboxylic acid of higher fatty acid. So when this alcohol and carboxylic acid reacts, then what we get is we get water. So how we get water? As I said, the OH of the acid and H of the alcohol combines, and you get 3 molecules of water. And what is left with? We are left with the ester. And this ester is made up of 3 stearic acids, and the alcohol is a glycerol, so it's known as glyceryl tristearate. And this glyceryl tristearate, if you look at the general equation, you say it's nothing but ester, but it's an ester of a higher fatty acids. And these esters are known as oils and fats, because if you look at the definition, it says oils and fats are esters of higher fatty acids. And these oils and fats are the raw material for the manufacture of soaps in our soaps that we use daily in our daily life. Okay, now let's see how these oils and fats are used in preparing or manufacturing soap. So it says When oils and fats are boiled with aqueous solution of sodium hydroxide or potassium hydroxide, they give sodium or potassium salt. And the sodium and potassium salt of those higher fatty acids are known as soap. And the process is known as a saponification. And as I said earlier, in Greek, the soap is known, in Latin, the Greek soap is known as sap, and that process is known as saponification. And if you remember clearly in lower classes, you must have learned about how this coconut oil and sodium hydroxide, when you heat together, you get a soap. So this is the same thing that happens here. So the reaction, so you have oil and fat together with sodium hydroxide, or you can use potassium hydroxide. So when these two are heated together, then what happens is you get sodium salt of the higher fatty acids and then a glycerol. This sodium salt of higher fatty acid is known as a soap, and the process, as I said, is known as a saponification. Okay, here is explore yourself. Now in daily life we use different types of soaps, some as a laundry soap, some as a toiletry soaps. So here are pictures of two soaps, one is a Lifebuoy and another is a Wheel. Now I want to explore further. What's the difference between these two soaps? Why can't a Wheel soap be used to wash our faces? And why don't we use this Lifebuoy soap to do the dishes or do the laundry? There must be certain differences in the chemical structure or the chemical composition. So I want you to explore further why this, what's the difference between, what are the differences between these two soaps. Okay, now let's go with the last derivatives of carboxylic acid known as acid anhydride. And the general formula of acid anhydride, RCO, then in the center you have O, then again RCO. So here the OH group is being replaced by RCOO, and where R is an alkyl group, and in case R is CH3, then what we get is we get a specific acid anhydride known as acetic anhydride. And you know why the name acetic, because if you look at the parent acid, you will see that the parent acid is acetic acid here, and uses of acetic anhydride. So this acetic anhydride is actually used in the manufacture of a compound known as acetyl salicylic acid. So how this acetyl salicylic acid is prepared? It's prepared by heating salicylic acid with acetic anhydride in presence of phosphoric acid. So when you heat these two together, then you get a compound known as acetyl salicylic acid. So let's say this is the salicylic acid that we have, and when you heat it with acetic anhydride, then what happens is the acetate part of the acetic anhydride and H of the salicylic acid will combine together to give you acetic acid, CH3COOH. Then the rest of the compound again joins together to give you acetyl salicylic acid. And what is the use of acetyl salicylic acid? The trade name of acetyl salicylic acid is aspirin, which we use in our daily life whenever we fall sick. Okay, so with this we are done with the main content. So let's recapitulate what we have done. So in the first case, we have learned about the definition of carboxylic acids and its classification based on number of carboxyl group or the nature group that is being attached to that one. So on that, based on that basis, we have found out that it can be aliphatic or aromatic, or it can be classified based as mono carboxylic acid, di or tricarboxylic acids. Then we have also seen that the OH part of the carboxylic acid is expandable. That means it can be replaced with some other substances. So when it is being replaced, then we get its derivatives. In case it is being replaced by this halogen, we get an acyl halide. In case OH is being replaced by amide group, we got acid amide. In case it was replaced by alkoxy group, then we got esters. And in case it was being replaced by this anhydride group, we got an acid anhydride. So this there were the 4 derivatives of carboxylic acid that we have got and studied. Then we have also seen the reactivity of derivative towards nucleophile substitution reaction. And as I said earlier, the reactivity of derivatives of carboxylic acid depend on the magnitude of positive charge that is present on a carbon. So if any substances that helps in increasing the magnitude of positive charge on the carbon, we have found out that the reactivity of the derivatives towards nucleophile substitution reaction is increased. And based on that one, we have found out that the acyl halide were the most reactive and the acid amide were the least reactive. And finally, we have studied the uses of derivatives. For example, let's say esters are being used as a artificial flavor in food because of its pleasant smell and taste. Then we have also seen that this acid anhydride, they were used in preparation of a medicine by the name aspirin. So with this, I come to the end of my lesson. Thank you. Karinchela.